Good morning, everybody. So midterm 3 happened since we last met. Hope it went well for you guys. I think test scores will be in today. I think they've been in most Friday afternoons. Average is north of 70 for this exam. I think it's in the 72% range or so. So better in average than midterm 2, so that's good. Heading into the final, I think our course average is going to be about an 80, which is also pretty good, meaning that about half of the class is on track for B or better. 20% final exam has a lot of points left to earn, so I think we can get even more into that B or better range. This is the first year of Chem 1210 that we've had an actual grade scale. I know from your guys' vantage point, you're probably like, what do you mean? We used to grade on a bell curve. So it used to be that the average grade was almost like always a C plus, maybe a B minus. But if you look in the syllabus, there's a grade scale. That's a grade scale that will be applied to your final grade at the end of the semester. It's actually not yet applied in Carmen. So if you look at your actual letter grade in Carmen, it's just using the 93, 90, 87 grade scale. So your letter grade in Carmen is actually a little bit better than what it's, well, depending on what the actual score is, but it's probably a little bit better than what Carmen says it is. And then Carmen's weighting isn't quite right, or like once we get all of our exam scores in, exam scores account for 62% of your grade. Right now they're only accounting for, once midterm 3's in, 14 times 3% of your grade. So exams have been a little bit underweighted on your grade until all the exam scores are in. But nevertheless, I'll send an equation out like we had after midterm 1 and midterm 2 that you can use to kind of calculate your weighted score using your exam average at 62% of the course. The other 38% of the course is the 20% lab, 10% homework, 8% recitation. All those items you guys are doing great in. The average in lab's almost a 90. Recitation average should be 100. I don't see why it wouldn't be, but it's like a 98 or 99%. And then the homework average is right now writing about 92, but I also haven't added in the extra credit assignments. If you guys have done some of those will get added in at the end of the semester. So scores will probably go up a little bit once those get added in. I'm also going to reopen the assignments in case anybody missed them from midterms 1, 2, and 3. So prior to midterms 1, 2, and 3, there were some like chapter, I forget how they appear to you guys, but they're called like dynamic study modules. They're sort of by chapter. If you had not gotten a chance to do those, then you'll be able to do those before the final. I'll repost those probably later today and send an announcement out about that. But the max homework score is unfortunately 100% though, so we can't go above 100% on the homework score. But that'll put the homework average close to probably 95 to 97% once all those scores are put into Carmen. Okay, so with that, we're going to head into chapter 10. Let me say one other thing about preparing for the final. So the final exam will be a cumulative exam, unlike midterms 2 and 3, which are just over, the 3 chapters heading into those exams. So for the final exam, I have a couple review packets. If you look at the chapter 10 to 12 daily quizzes, there eventually are some like review packets within those. There probably, I would imagine, are a lot of chapter review packets from midterms 1 through 3 that you probably didn't exhaust when you were studying for those exams. So you can go back through some of the daily quizzes that are up there that you hadn't done already. If you're one of the maybe like 5 students who did all the quizzes, congratulations, that's amazing. But there will be a couple combined practice finals that the department posts when we get about a week or so out from the final exam. In terms of reviewing, I would review the chapter summaries at the end of each chapter. That page summary is a really good summary. It should kind of like give you a good rundown of everything that was in the chapter. And then you can go cite read anything that you've forgotten about. A lot of this stuff gets reinforced, so I don't think that for the most part there's a lot of forgetting of the chapters like 1 through 9 stuff when we get close to the final, because we do reinforce a lot of the topics that we cover. But chapter reviews are a good place to look. And then if you look at the chapter review, there's some suggested problems with that come up within those too. Or you can look at some of the SAEs, the exam prep questions you haven't exhausted, or just go back through some of those. End of chapter problems are useful for some students. You can look at some of the end of chapters. The red problems are answered in the end matter, so you can look at some of those as well. Okay, so heading into chapter 10, chapters 10, 11, and 12 kind of set the final sort of set of topics for Chem 1210 on gases for chapter 10, liquids for chapter 11, and of course solids for chapter 12. 3 chapters left to go, 7 lectures to cover them. We're only going to spend about 1 lecture on chapter 12 though, so we're just going to cover some select topics out of chapter 12. So chapter 10 on gases, what we're going to talk about are some characteristics of gases, The ideal gas law. I suspect a lot of you guys have seen the ideal gas law equation. Have you guys seen PV is equal to nRT, often called PIV-NERT? So we'll see this equation here in this chapter, some utility of this equation. So we'll talk about ideal gases. So an ideal gas is a gas where the particles aren't interacting with each other. And it's also a gas where the particles are occupying a very negligible portion of the container. So in a gas, the particles are very far away from each other. So the particles are far away from each other. They're not occupying a large portion of the container, and they're also not interacting with each other. So we'll talk about gas mixtures and partial pressures so we can understand things like air. Of course, air is a good example of a gas mixture. About 78% nitrogen, 21% oxygen. Does anybody know the next most abundant component in air after oxygen? Well, nitrogen's the most. So nitrogen's about 78%, oxygen 21%. Actually, argon is the next most abundant substance in air. It's about 1% is actually argon. Interestingly, nitrogen, oxygen, argon, almost 100% of the atmosphere don't absorb infrared light. Just infrared light goes right through a sample. Now, the reason why that might be important is that means that most of air cannot act as a greenhouse gas. So if you think of a greenhouse gas as being able to absorb heat, absorb infrared radiation, only things like CO2, water vapor, CH4, hydrocarbons, things like that in the atmosphere, those molecules are capable of absorbing infrared light and trapping heat within the atmosphere. So, but 99% plus of the atmosphere, though, is invisible to that process. Just like a small artifact of the consequence of the components of air. So then we'll talk about kinetic molecular theory of gases, try to understand how gases behave a little bit better with that theory, and then talk about effusion and diffusion. Effusion is how gases escape from a pinhole, and diffusion is how gases like travel through a medium. So the smell of cooking, making it from one side of the house to the other, is diffusion. And then finally, we'll talk about deviations from ideal gas behavior when we talk about things we might call real gases. So if an ideal gas is the non-interacting particle, the real gas is the particles that start interacting with each other. Real gases are approaching liquids. So this is thinking about droplets that start to form, molecules that start to be attracted to each other as we start to approach that liquid phase. And this will lead right into our liquid chapter. So getting started on some characteristics of gases. The physical properties of gases are mostly the same, right? They are comprised mainly of nonmetallic elements, so are things like hydrogen, nitrogen, oxygen, et cetera. They conform to the shape of their container. They are highly compressible. You can take like a gas container with a piston and compress the gas, and that would, of course, increase the pressure of the gas sample. Gases have low densities. The mass to volume ratio, of course, is going to be very low because there's not much mass occupying the sample of the container of a given volume. So we have a relatively low density, so low densities of gases. And then whenever we have two or more gases mixed together, then they have to mix in a homogeneous fashion, so meaning that they just mix equally or completely randomly. And this is also, it would take them interacting in some sort of fashion to get a heterogeneous mixture. So we're not going to get a gas where one gas is on one side of a container, another gas is on another. Sort of naturally, the gas particles are going to equally distribute amongst each other. And so then the properties that define the gas sample from the ideal gas law that we wrote earlier are the temperature, pressure, volume, and then the amount of gas, which we often use as the moles. And so the moles has the symbol N. And this is kind of jumping a little bit ahead. We do a small derivation of the ideal gas law equation in a couple of slides from now. But I think we've all, or probably a lot of us, have seen this equation before. And so, of course, we're just relating the pressure times the volume is equal to the moles times temperature, and then times R, where R is the ideal gas constant. I don't want to bog us down with trying to memorize what R is equal to in some different units just yet, so we'll just leave R alone for now, but it's just a constant that we could express with some given units. So we'll talk about what those units might be in a derivation of R in a few moments. So then pressure, just the sort of definition of pressure is it's the force that's applied to an area And so you can think of just an equation for that pressure is just force divided by area. Now, you can think about the atmospheric pressure that's exerting its force onto the surface area of Earth. And so you can think about the atmosphere, how it's exerting a pressure due to gravity being the accelerative force. And so we can think about gravity sort of having an impact on the amount of air. So the amount of air per square meter, if you take a square meter column of air straight up in the atmosphere, that would actually be about 10 to the 4 kilograms of mass would be above every square meter on the surface of Earth. And then that 10 to the 4 kilograms, as we think of force being mass times acceleration, so that mass is being accelerated towards the surface of Earth where the acceleration is gravity. And so you can think about this being the gravity on the surface area of Earth. So that accelerates that mass onto the surface of Earth so that the standard pressure is about 10 to the 5. So since gravity is about close to 10 times 10 to the 4, and this is approximately here, that this works out to be approximately equal to 10 to the 5. And this was the pressure that was being exerted onto a square meter. And so the way the units work is that this would be a kilogram, meter to the minus 1, second to the minus 2. Because we took kilograms times meters, divide by seconds squared, and then divided by the surface area of a meter squared. I'm only just trying to do this to show you that you have some fundamental connection of SI units, of the kilogram, the meter, and the second, to what ends up being the SI unit of pressure, where this 1 kilogram, meter to the minus 1, second to the minus 2, is equal to 1 Pascal. And that's the SI unit of pressure. And interestingly, the Pascal is probably the least used unit of pressure. I mean, it's used in some circumstances. It's used a lot in gas cylinders on the gauges of how much gas is within a gas cylinder. But that's probably the only practical use of Pascal in common units. When we think of atmospheric pressure, we tend to think of things like inches of mercury, maybe if you're like a meteorologist, if you're looking it up on like the Weather Channel or something. You might look up the millimeters of mercury is another way of measuring atmospheric pressure. Another unit of pressure is millimeters of mercury. And then there's some other units as well, like ATM or atmospheres, that are common units that we use in a lot of different problems. But atmospheric pressure is just a pressure that's being exerted by the atmosphere's mass onto the surface area of Earth due to gravity. And so as we start thinking about pressure, we can sort of think, okay, that's like ordinary pressure. Then we can think about some conversions to other pressure. And so hopefully the example of atmospheric pressure is just getting us thinking about the units of pressure, that our SI unit of pressure being the Pascal, that the standard atmospheric pressure is about 10 to the 5. More precisely, the standard atmospheric pressure unit that we call 1 ATM, like a standard atmosphere or 1 ATM, is equal to 101,325 Pascal. Not worth memorizing, but that just is like the precise conversion over to that SI unit of pressure. And so this is that SI unit of pressure, is that Pascal. And so then 1 atmosphere is also equal to 760 torr. I don't know if you've ever heard the unit torr before, but this is exact. So exactly 760 torr in 1 atmosphere. Also exactly 760 millimeters of mercury. Kind of peculiar that you have a unit of torr and millimeter of mercury that are exactly synonymous with each other, yet somehow those units are used somewhat in different circumstances. Now, the millimeters of mercury, where it comes into play, or like why that's a unit, you may think at first glance, why would there be some unit of millimeters, or some length unit of some element? Well, the way that you can measure an atmospheric pressure is if you took a vacuum, like take a vacuum to a tube, so vacuum all the air out of a tube, and take the tube into like a dish of mercury. And so that dish of mercury has the atmosphere pressing down on it, and then it has nothing pressing down in the tube. So the tube, the mercury is going to go up the tube until the height of mercury, that the mass of mercury in that tube is equal to the mass of air that would be above that sort of volume or that sort of surface area of the tube. So if you think of however much volume of mercury is in here, that's the same, that's going to relate to how much mass of mercury is in that tube, that's going to relate to the mass of air that's pressing downward onto that mercury dish. And so the amount of mercury that gets pulled up is just equal to or related to whatever the atmospheric pressure is that day. Now, why you use mercury is because it's really has a high density. And so if you think of how much mercury it takes to sort of counterbalance the mass of air, that you're sort of taking the ratio of, for like a square meter, let's say, that's 10,000 kilograms, or 10 to the 4 kilograms. That we need to get 10 to the 4 kilograms of mercury if we wanted to have a 1 meter by 1 meter column of mercury. So if we wanted to have a column of mercury, we'd have to think of how high do we need that to be if it's 1 meter by 1 meter in order for there to be 10 to the 4 kilograms of mercury that are going to get pulled up into that tube. Well, if you make the tube small, then that's going to reduce the mass of mercury. So that's one thing you do is make the tube small. And then instead of using something like water or some other component that has a lower density, if we used water, we'd have to have a column that's like 13 times higher because the density of mercury is about 13.5 grams per milliliter. Like water is only 1 gram per milliliter. So if we think, okay, so whatever the height of mercury is that we need, that if we chose water instead, it's going to have to be 13.5 times higher. And so then you figure out, okay, how high is that column of mercury going to be? The answer is 760 millimeters. So 760 millimeters is, yay big, it's like that. And so if you think 13.5 times as high, that's going to be a pretty high column. And so we chose mercury. Mercury was chosen for this task because it has that super high density, and it makes for a really small, relatively speaking, column. And so then you can have other units like inches of mercury. Like I mentioned before, meteorology often uses the unit of inches of mercury. So if you convert millimeters to inches, then that would be the inches of mercury. I don't know the number exactly, but it's around 30 inches of mercury would be 760 millimeters. Okay, and so that's the sort of millimeter mercury unit is. It's related to the barometer and how much mercury you would need to measure the atmospheric pressure. So you're taking this height here as being related to atmospheric pressure. So imagine atmospheric pressure is higher on a given day. So if you have more pressure pressing down, then the height goes up in the mercury column. So more mercury is needed in the column to counterbalance atmospheric pressure. You'd read a greater height, and then you'd have a higher pressure. Now, we rarely, or probably never going to read a barometer in this class. This is just to understand why there's some different pressure units. On the next slide, we'll go through a couple conversions to see how we convert to and from these units. Another unit that really never gets used in this class, but millibar sometimes gets used in meteorology as well, is the unit of bar. That 1 bar is equal to 1.01325. So it's kind of like the Pascal, but divided by 10 to the 5. And then another unit that's commonly used on gauges, you use on your tire gauge. I just used one yesterday because how many of you guys, well, I don't know how many of you guys have cars on campus? Did any of you guys have the tire light indicator go off in the last week when it got cold out? I don't know, sometimes this happens. When it gets cold, your tire pressure obviously drops a little bit. And if it goes below the sensor on your tires, then you gotta go put some air in your tires, get this stupid light to turn off in your car. And it's always like 31 PSI instead of 32. It's like, come on, it's not that big of a deal. But so the PSI, pounds per square inch, is the gauge reading that you often use on dealing with filling tires or things like that. So let's look at converting some units here. So let's convert a pressure. If we have used some sort of a tool to determine that the pressure of a gas sample is 745.0 torr, let's convert that to millimeters of mercury. Let's convert that to ATM, Pascal, into PSI. And then these conversion factors aren't worth memorizing either. If you need these conversion factors, they would be given on a test. The only one that you'll probably use a lot is that 1 ATM is exactly 760 torr, and that this is also equal to 760 millimeters of mercury. So those two conversions, you're probably going to use those so often that you come to memorize those values. But when converting to millimeters of mercury, you see that they're exactly synonymous with each other. So that I don't think we even need to do any work here to see that this would be 745 millimeters of mercury. Like if you need to do the conversion, you might say, well, 745 torr, well, 760 torr is an ATM, and the 1 ATM is 760 millimeters of mercury. So if we're like converting to ATM and then to millimeters, we're dividing by 760, then multiplying by 760. So we get exactly the same number of millimeters of mercury. So millimeters of mercury and torr numerically are the same as each other. And it is strange that there's two units that would be the same as each other. So it's weird that this exists with these two units, but they get used a lot in examples. So some examples will use millimeters of mercury, some will use torr. Then the ATM, we could just do 745.0 torr, and then just 760 torr is exactly 1 ATM. And so we don't have to round to 2 sig figs. We're going to keep all 4 sig figs because that's an exact conversion. So it's 0.9803. So that's a little less than standard atmospheric pressure of 1 ATM or 760 torr. Pascal. Now, the way we can do the conversion is, the way we were told, is that 1 ATM is 101.325. But we also know that 1 ATM is 760 torr. So 760 torr is an ATM. And there's always 2 ways we can do this. Like the long way is to then write out an ATM is 101.325 Pascal. But I always like the simple way of just doing it like this, of saying, well, 760 torr is an ATM, and ATM is 101.325 Pascal. So we can do that in one step. So 101.325 Pascal is equal to 760 torr. So 745 divided by 760 times 101.325. Now you could have also just taken the ATM above and multiplied by 1 ATM is 101.325 Pascal as well. So we could have started with this value here and just went straight to Pascal as well and gotten the same value. So I get 99,325. .2, and then this just has to be rounded to 4 sig figs. Good sig fig review, I guess, would be that this would be 99,330 Pascal, or 9.933 times 10 to the 1234 Pascal. Now, in going to PSI, let's actually use the ATM value here. So in converting to PSI, we'll take the 0.9803 ATM, and then 1 ATM is 14.696 PSI. So it's close to 15. That's 14.41. Now, like I said, PSI is most often used in filling tires. One interesting thing is when you fill your tires, that this isn't all that big of a deal. It's more like practically important than anything. And it kind of came up during that Tom Brady, like the Deflategate scandal too, is that a pressure gauge is a gauge reading. It's the pressure above atmospheric pressure. So when you see that your tire has 32 PSI in it, it's 32 PSI on top of atmospheric pressure. So it would be 32 PSI plus about 14.7 PSI for standard atmospheric pressure, and slightly different because standard pressure may vary based on your location. So when we read a gauge, it's the pressure above atmospheric pressure. And so like when your tire is empty, it doesn't have 0. air in it. It has 1 atmosphere in it. So it's the pressure above atmospheric pressure you're reading with your gauge. Yeah.
When you say 760 mmHg, what's the diameter of the tube? Any diameter is still?
Well, it's like the diameter of the tube, the mass that's in that tube has to be equal to the mass that would be above that cross section.
So if you take a large diameter tube, it's still show 760 mmHg?
Yeah, exactly. So if you use a huge column, then you would still have to have it 760 millimeters. Because like that, so if you think of like the volume in the tube, and then if you think of the surface area of the tube, that's the pressure pressing down that surface area, kind of counterbalancing air. So that mercury is just counterbalancing the mass of the atmosphere. So yeah, so the height of the column is what matters. So yeah, if you use a skinnier column, less mercury is used, that's good. So you're using less of a relatively expensive metal. Mercury is hazardous, so there's other ways of measuring atmospheric pressure without using mercury these days, though. Okay, so the pressure of it's kind of funny, the way you determine the pressure of a gas sample is really using a gauge or something. Or like using like a digital gauge reader these days and not really like an actual device like a manometer. But a manometer is really just a relatively simple device. What a manometer is it's a U-tube, like an actual U-tube filled with mercury, not a video. But what you would start with is a column that has equal amounts of mercury with your gas valve closed. So you have this valve closed. You have your mercury heights equal. And then you can imagine you have a gas sample connected to this tube, and the gas sample could be one of two situations. It could either be under a vacuum, so you could have a vacuum in that gas sample, or you could have a pressurized gas sample. I suppose you could also have a gas sample at exactly atmospheric pressure. So imagine you have your mercury heights equal, you open the valve, so if you open this valve, and the gas sample happens to be rated atmospheric pressure, then nothing happens, right? So the heights would stay the same. So if the gas sample is at atmospheric pressure, then it would just look like this. The heights of the columns would be exactly the same. Then if you open the gas sample and the gas is under a pressure, so if the gas has a pressure above atmospheric pressure, it's going to exert that force on the mercury and it's going to press the mercury downward like it's showing in the column in the example. And so in this example here, the pressure in the gas sample is greater than atmospheric pressure. And then if the gas sample does the opposite, if it does, it looks like this, where the column is higher here and lower here after we open that valve, then that would be the pressure of our gas being less than atmospheric pressure. And so you can imagine the three situations. The gas is right at atmospheric pressure, the gas is at a high pressure, and the gas is less than atmospheric pressure. And the way you can actually calculate the pressure is to take the height differential. And again, you tend to use mercury or something relatively high in density so that this doesn't have to be, so this would actually be a pretty big column. So this would be a fairly big column, so you can measure a wide range of pressures. And so then what you would measure is the pressure of the height in like units of mercury. So you would measure the distance of height in millimeters, and you're either adding that in the case of the gas being above atmospheric pressure, or you're subtracting it when the gas is below atmospheric pressure. So if you think of your atmospheric pressure in something like millimeters of mercury, then you can see that you want to put the height difference in millimeters of mercury as well. So you measure literally the millimeters of mercury difference between those two heights. And so that's where you can see measuring the height in millimeters, or if you are given that value in centimeters or some other value, you just convert it to millimeters, and then you would convert or use the pressure of atmospheric pressure in millimeters of mercury. So you're literally thinking of the height differential in units of mercury, and the height differential in mercury, so how, to give you a means of calculating the pressure of your gas sample. This isn't a super common problem. I don't think this isn't something that we need to really do an example of. This is just like a thought example of how you would measure a gas sample. So pressurized versus vacuum versus at exactly atmospheric pressure using a manometer. Example. Yeah, so like this. Okay, now I think you could also understand that probably most gas samples practically are measured using just a digital gauge anymore. So there's more modern ways you can measure gas sample pressures than using a tube filled with a hazardous metal that's in its liquid form. But anyways, so let's talk about some gas laws. So how pressure and volume and temperature and volume and quantity are related to each other are what we call the gas laws. And this is how originally the sort of relationship between these variables was studied. So Boyle came along and found that volume and pressure had an inverse relationship, meaning if you took a gas sample and you could imagine decreasing the volume. So you take a gas sample, it has whatever volume. If you start decreasing the volume with like a piston, you're increasing the pressure. And so by decreasing the volume, we increase the pressure. So our pressure is becoming higher as we go to a lower volume. So go to a lower volume, we're going to higher pressures. So we get this inverse relationship between volume and pressure. So again, if you think of having a relatively big volume of a gas, if you compress the gas to a smaller volume, so as your volume goes down, then your pressure is going to go up. And so that means we have an inverse relationship between volume and pressure. You can then also think if you had like a balloon that you could change the temperature of. So you have a balloon, you can make the balloon warmer, it's going to expand. And so volume and temperature have a direct relationship with each other. So if you can take some sort of a balloon, expand its volume, then the temperature goes up. So we go to as we go to higher temperature, we go to a higher volume. So we get a direct relationship between volume and temperature, and I think that kind of makes sense. So I think both of these relationships make fundamental sense. But Charles and Boyle were studying these and trying to come up with the actual relationship between these. Back up and say that from the relationship, what you can write is that like V over P is going to be equal to a constant. And then what that allows you to do is to say if you change the volume and pressure without changing anything else. And so this would be constant N and constant T. So if you can change the volume and then subsequently change the pressure as a result, and then you're keeping constant the quantity, you don't have an air leak in your container, you're not changing the temperature, then this allows you to see that V1 over P1, some initial set of volume and pressures, would be equal to some final set of volume in P2. So V1 divided by P1 is equal to V2 divided by P2. So that there can just be like a simple relationship between some initial set of volume and pressures and the final set of volume and pressures. Yeah, I actually, hold on. Well, this is actually the wrong relationship. So hold on. This is technically, I need to multiply P over to this side. So P times V is equal to the constant. So PV, not P divided by V. So P times V is the constant. And so that means P1 times V1 is equal to P2 times V2. And we're going to see how we're going to get these relationships as well from the ideal gas law. So if we look at the ideal gas law, you would see this too, that PV is equal to nRT. And so if you think of the full ideal gas law, since we've already kind of mentioned it, that if these are staying constant, we have P1 and V1, and nRT are constant. Then if we change P2 and V2, they're still equal to nRT. nRT are still the same. So then P2 times V2 are still equal to nRT. So then P1 times V1 are equal to P2 times V2 because they're both equal to the same nRT. So this makes P1 V1 equal to P2 V2. So you can look at the ideal gas law and get this relationship as well. And then the V over T is where we get that inverse relation, or the direct relationship. So we get the V over T relationship being equal to a constant. So V1 over T1 is equal to V2 over T2. And then you can also get this relationship from the ideal gas law. So if we take PV is equal to nRT, if we do V divided by T is equal to RT divided by P. So if I just rearrange the equation for V over T and then throw a 1 and 1 here, and then if these constants remain constant throughout a change in volume and temperature, then they're going to be equal to V2 times T2. So hence V1 over T1 is equal to V2 over T2. Yeah.
The relationship between pressure and volume, it's a curve, it's not linear. Does it mean that constant changes at different pressure and different volumes?
No, I think it's just a consequence of like a 1 over x graph just will look like that. You know, so like anytime you have like a plot of that's y is equal to x is a straight line. But if you have a plot of y is 1 over x, it's just a curved line. So it's just a consequence of the inverse of pressure. So it's really not, and like you wouldn't expect it to be a straight line. Like a negative straight line would be where you have, the relationship would be that would be like y is equal to negative x, not 1 over x, if that makes sense. So to have a curve that looks like this mathematically would just be y is equal to minus x, and then there'd be some constant to bring that above 0. Yeah, and so then if you just had the plot of y is equal to 1 over x, and that would be the plot that looks like that. So it's just a consequence of the 1 over p. But yeah, good question. So V1 over T1 equals V2 over T2. Again, coming from the ideal gas law, just a relationship of V over T's being equal to the same set of constants before and after a change. And okay, so then we can look at problems like this one here of having a 2-liter gas sample at 2 atmospheres. What pressure would the sample have if the volume of the gas is reduced to 1 liter? So we have a P1 V1 equal to P2 V2 problem. And so we have our P1 times V1. Let's do the pressure first. 2.00 atm times 2.00 liters equal to P2 times V2. And our V2 is being changed to 1 liter. So we can solve for P2, but then we can also make sure to think of what we're doing. So we have 2 liters of gas, and we're compressing it. So the pressure should go up. So the pressure is going to go up here. And so we're going to have 4 atm times liters divided by 1 liter when we do the math here. So our volume's canceling. So I get P2 is equal to 4 atm. But I think the 2 keys are one, seeing that it's going to go up just from the inverse relationship of pressure and volume. And then the other thing is actually calculating it, is seeing the P1 V1 equals P2 V2 being used to solve the problem. So let's look at a V over T problem. Now, the temperature is where we have a little bit of an issue, if you will, where if temperature goes negative, we have a bit of a problem. You know, so like if we think of going from 25 degrees C to negative 25 degrees C, that negative sign is going to mess everything up, unless we go to like an absolute temperature scale, where the absolute temperature scale would prevent temperature from going negative. So absolute 0 Kelvin is the lowest possible temperature that a substance can reach. And so if we use something like the Kelvin scale, then that would sort of get rid of the problem of temperature going negative. And so one of the things that we're going to have to do when we think of any problem using PV is equal to nRT is that temperature is going to have to be in an absolute scale. And something like Kelvin. Technically, like the temperature scale, the absolute scale based on Fahrenheit, does anybody know the name of that? I think it's Rankine or something like that, but it's not a very common scale. But there's an absolute scale that's based on Fahrenheit. And it's like minus 456, something like that, degrees Fahrenheit is absolute 0. So it's a scale that's like subtracting that off of the Fahrenheit temperatures. And so we just need to use an absolute scale where temperatures are always positive. So temperatures can't go below 0 Kelvin. And so when we look at a problem like this where we have our V1 over T1 equal to V2 over T2, and we have a gas sample 2 liters at a constant pressure, such as in a container with a movable piston. So we have this at 25 degrees C and we warm it up. So you imagine you have a container that maybe you can put into a water bath where you heat up the water bath, and there's just a movable piston that's going to keep a constant pressure. And so then what is the volume of the gas sample? And the volume of the gas sample should increase, right? So we should be increasing our volume due to the direct relationship. So increase the temperature, increase the volume. And so then when we go to solve here, we're going to solve for V2. And so what we're going to have to do is we're going to have to convert to Kelvin. In fact, if you don't convert to Kelvin, you're going to see you get a pretty widely different volume change. So if we do V1, so 2 liters, and then times 25, and then the conversion to Kelvin is 273.15. To go to Kelvin, so it'd be 298.15 rounded back down to 298 Kelvin. So this in Kelvin would be, if I just do that math real quick, this would be 298 Kelvin. Then we're going to divide that by 50.0. Actually, it would be 298.2 Kelvin. Let's actually keep it as 0.15. So the exact conversion is temperature in degrees C plus 273.15. And so it does say 25.0. So we'll keep the 0.15 on for the ride. It's good to 4 placeholders. 50.0 degrees C. I'm already screwing up. I'm screwing up so many times today. My apologies. I got to divide by T1. So we're dividing by 25.0 plus 273.15. So that's our T1. T2 is 50. So T2 is 50 plus 273. And then sometimes you may wonder, do you have to convert to Kelvin? And you do, because you would get a different temperature if you don't, or you get a different volume if we don't. If you notice, like, let's run this math here real quick and compare if we convert or don't convert. So we do 2 times the quantity 50 plus 273.15, and then divide by quantity 25 plus 273.15. And so we said that would expand the volume. It expands it to 2.17. And so if you imagine a balloon becomes a little warmer, it expands a little bit. It doesn't double in volume from doubling this temperature. It just would go up a little bit because we're not really doubling the temperature, because you think of the absolute scale, we're only increasing the temperature by a relatively small amount compared to 50 versus 25 in the absolute temperature scale. Now, if you also then think, if you go from like negative 25 to 25, that negative sign, we can't like throw a negative sign in these calculations. We're not going to flip to like a negative volume just because we go below 0 in the Celsius scale. So we have to use that Kelvin scale. Now, if we had not converted, we would have went with 4 liters as the answer. And so 4 liters is just too big of a volume change. I see 2.17 isn't a choice. Maybe I screwed up again. Now, I think there must not be a correct answer available. But 2.17 liters would be what that should be changed to. So that should be 2.17 liters. So again, we got to convert to Kelvin in almost every problem in this chapter. I can't think of any problem in chapter 10 where we don't convert to the Kelvin scale. Okay, so let's talk about the relationship between quantity and volume. This one's a pretty obvious one, right? That if you have less gas in a balloon, it's going to be a smaller balloon, you know? So as you put more gas into a balloon, when we think of putting the quantity of moles in, then the volume would increase. So more gas in the balloon, bigger balloon. Okay, now one of the other consequences of this is if you think of having an equal volume, so if you take an equal volume of, say, 3 different gases, we have helium, nitrogen, and CH4 as example here, and you have 1 atmosphere of each of these gases, and you have them at the same temperature as each other. We go to 0 degrees C. Oddly, these are called STP, like standard temperature and pressure. Like, sometimes we used to test this. I don't think we test this anymore. It's a silly concept, and it's a trick question. If we ever say, what's so-and-so at STP, the weird thing is that the temperature of standard temperature and pressure is 0 degrees C. And well, I don't know why we would use that as a gotcha, because everybody would think standard temperature is 25 degrees C. But if we ever refer to STP, this is 0 degrees C, and 1 ATM. So I would veto any question on the test that had that used as a question of trying to catch you guys off guard on STP being 25 or 0 degrees C. But just know if you see an example in the book, or if you're looking data up online or something, that STP is actually 0 degrees C. But so at STP, these four gases have the same volume, but when we have these particular amounts of the gases, when we have 4 grams of helium, 28 grams of nitrogen, and 16.0 grams of CH4. Now those masses obviously are different from each other, but those masses correspond to 1 mole. That each of these, the grams per mole of helium is about 4 grams per mole, nitrogen 28.0 grams per mole, so this is 1 mole of N2, and then CH4 16.0 grams per mole, this is 1 mole of CH4. So when you take 1 mole of each of those gases, which of course have a different mass because they have different molar masses, that what's the same, the property that those gas samples have with each other is they have the same number of particles. So the helium sample has an Avogadro's number of helium atoms because there's a mole. So 1 mole of helium is 1 mole of helium atoms. If we have a mole of N2, then we have an Avogadro's number of N2 molecules. So 1 mole of N2, 6.022 times 10 to the 23 N2 molecules. And then the sample of CH4 also has the same number of particles, the particle being the molecule of CH4. So we have 6.02 times 10 to the 23 molecules of CH4. Now, obviously the CH4 sample has a lot more atoms because each molecule of CH4 has 5 atoms, only 2 for N2, just 1 for helium. So we have way more atoms in the CH4 sample, but they're connected together. It's the particles as they're connected together that matter here. And so these samples all have an equal number of particles, they have an equal number of moles, but of course a different mass. And the different masses are based on their different molar masses. And so then those give those gases the same volume at STP. So the volume of any gas at STP, as long as it's behaving ideally, so an ideal gas at STP is going to have a volume more precisely of about 22.415 liters. So they all have the same volume. And this is talking about Avogadro, and this kind of led to this discovery of Avogadro's number. And so we call this Avogadro's law of the relationship between volume and quantity.
My head around that. Nitrogen is atomic number 7. Helium is just 2. It's more than 2 times at the atomic level, but still occupying the same space.
Yep. And it's because of this that helium is 4 grams per mole, and N2 is 28.0 grams per mole. And so that what they have in common is that these gas samples have the common that they're 1 mole. And what gives a gas property, or what gives a gas its properties, is how many particles there are, not what the particles are themselves. So the identity of the gas is almost irrelevant. What matters is how much in terms of particles. And then the particles is the actual molecule, or the atom. So like, what is the particle here? The particle for helium is the helium atom, and N2 is the N2 molecule. So what matters is how many molecules or particles there are in the gas sample. And this, I think, makes sense because if the ideal gas are non-interacting particles, it's just a question of how many particles do you have. And so that's what really tells you and defines the property of the gas sample is what's the pressure, what's the volume, and then what's the temperature, and then how much gas. And how much isn't really, it's not the mass that you really need to know, it's the moles you need to know, or the particles. The number of particles or the number of moles.
So extending this, we come up with some new particle which is like 100 times more than nitrogen. It'll still occupy the same volume.
Well, other than you run into the question of would that still behave ideally? Would that start to lead to breakdowns? So the bigger a gas particle becomes, the more attracted to itself it becomes. Like we're going to see that most of your gas samples are relatively non-polar substances. We can have some polar substances that are gases, but most gases are on the non-polar side. We learned that non-polar molecules don't have those maybe built-in charges that like water and other molecules have, or like a built-in dipole. So they have a weaker attraction. This gets into the liquids chapter a little bit. But if 2 particles have a weaker attraction, then they're not going to be attracted to each other. If you make them bigger, they're going to have a greater attraction. So you're just making the particles more likely to be a liquid at, say, whatever temperature you're at. So how do you, like if the particles just aren't in the gas phase and they're liquid, then that's kind of telling you something. That's telling you that they were more attracted, and then they just remove themselves from the gas phase altogether. The other thing is, if you just rearrange the equation, V, so the volume of the gas is equal, from PV is equal to nRT. And so if you take V is equal to nRT divided by P, then you can kind of see here, if you have a mole at the same temperature, at the same pressure, you get the same volume. So if you just think of the ideal gas law, that for any gas, for anything that's actually a gas that behaves ideally, then the volume is equal to nRT divided by P, which would be the same equation for all gases. And so let's put these together. Yeah? Okay, so let's put these equations together from Avogadro's law to Charles' law to Avogadro's law. So Boyle's, Charles, Avogadro's. So inversely proportional to pressure, directly to temperature, direct to moles, leads to volume is directly proportional to NT divided by P. So just putting these sort of three equations together. And so then what this would mean is if we take, PV over NT, that's equal to a constant. Just kind of like what we were saying before, like we've gotten rid of all the other physical constants. And so then this is where that ideal gas constant R comes into play. That we set the PV over NT equal to the gas constant R. We then rearrange it for Pivnert for an equation that we use more commonly. And so PV is equal to nRT, ideal gas law equation, is then an equation for relating these four properties for a given gas sample. Now let's talk about the units of R for a minute. And so we can actually go back to the ideal gas. So a little bit more precisely, if you have 1 mole of an ideal gas, it occupies, it's about 22.414 liters at STP, at 0 degrees C and 1 ATM. And what that allows you to do is to calculate R, because you know all four of our values here. So we can calculate R. So R should be equal to PV divided by NT. And so we know that the pressure of the gas sample is 1 atmosphere. We know the volume it occupies is 22.414 liters, and that was 1 mole. And then we knew that that was 0 degrees C, not 298 Kelvin, but 273.15 Kelvin. And so then if you throw all that into a calculator, that is the 0.08206 unit, which if you've ever done a problem with the ideal gas law, you might have seen or recalled those units. But the units being liter atmosphere, so liter atmosphere per mole Kelvin. So mole times Kelvin. So those are probably the most common units of R. I think we do give that on tests, but we'll use this so much, if you don't memorize it, probably something went wrong. So once you do about 5 or 10 examples of this or so, I think you'll certainly commit that value to memory, at least long enough for the final exam. And so that's our units in liter atmospheres per mole Kelvin. And there's some other units, and like at times in the class I would actually go through and calculate how we get this number here. I actually will do that when we need it later. So we actually don't use this unit until the sort of tail end of the chapter. So I'll come back and I'll sort of derive this later. But it kind of just comes from the derivation of the gas constant, where we convert these quantities here to SI units. So if you go to like cubic meters, and if you go to from atmospheres over to Pascal. So if you convert pressure and volume to like SI units, then you get the SI units of R to pop out of the equation. So I think what's really useful now to see is that these units here, so these, the liter atmosphere mole Kelvin units, let me circle them here, that these are the non-SI units. So that's like the non-SI unit version of R. If we ever need to calculate things in SI units, we need to use the SI unit version of R. And that would be this number here. And so if in the back of our mind is we have like a non-SI, because atmospheres is not the SI unit of pressure, and cubic meters is the full true like SI unit of volume. And so if we want things in SI units, we're going to switch over to 8.314. Non-SI units are predominantly how we solve most problems before we get to the end of the chapter. So we use this one more often in this chapter. And then we could convert like ATM to torr, and then have like a liter torr per mole Kelvin. But we'll never give this value to you on a test, because what you can do is if we say what's the, use the ideal gas law to calculate the volume of a gas. So if you got to calculate volume, it would be nRT divided by P. And so if we give you the pressure in torr, you can just convert it to ATM and then use the usual ATM, liter atmospheres per mole Kelvin unit of R. So you can change R's units given a different pressure unit, or you can just change the pressure to ATM and then just use that same unit of R that we always use. And so then temperature is always going to Kelvin in these problems too. So we're always taking temperature to the Kelvin scale. Okay, so there's a couple different units. One other thing to wrap up with today is that we can relate to density. In fact, I think we're at time. So that'll be good for today. So we'll get into calculating densities with the ideal gas law next time. All right, guys, have a great weekend, and I'll see you back here on Monday.